The Drifting Worlds, a Chronicle of Solar Evolution. Chapter 1, The Theory of Drifting Worlds. There is a theory whispered among the oldest astronomers, a tale far older than textbooks and far bolder than any accepted model of planetary formation. It begins with a restless sun, not the serene glowing orb humanity sees each morning, but a primeval, molten titan capable of sculpting worlds from its own burning flesh. According to this ancient idea, the sun is not merely a star around which planets happen to orbit, but the very parent of each world, forging them from eruptions of its own incandescent body. And as the eons unfold, those worlds drift ever outward, cooling and transforming in a slow cosmic pilgrimage away from their maker. In this theory, stars like the Sun occasionally unleash great molten ejections, titanic arcs of plasma and heavy elements thrown into the surrounding void. Most vanish into the darkness, dispersing like sparks from a bonfire. But some of these ejections slow, compress, and begin to coagulate. Gravity clenches them together, turning liquid fire into molten rock. In the beginning, such newborn worlds are blistered, glowing, and violent, no different from what Mercury is now, a burnt cinder trembling close to the solar inferno. These new planets vibrate with heat, lacking atmospheres, lacking surface stability, barely distinguishable from the star that birthed them. But over millions of years, everything changes. As these infant planets orbit the Sun, they are gradually pushed outward, by solar winds, magnetic interactions, and the subtle exchange of angular momentum. Bit by bit, each world drifts away from the star's furnace. And with distance comes transformation. What was once molten cools. What was once solid releases vapor. Minerals boil out gases. Atmospheres begin to appear like fragile halos. In this stage, the planets resemble a young Venus, oppressive skies, crushing pressure, and storms that never cease. The theory suggests that as planets continue their outward migration, they pass through phases of decreasing temperature. The thick, toxic skies eventually cool enough to condense, then rain, then balance. Water forms oceans. Clouds separate into delicate systems. Surface crust stabilizes. The planet becomes something like Earth, a narrow temperate window in its long exodus from heat to cold. Life may flourish briefly in this moment of balance, a fleeting equilibrium before the world drifts farther still. And farther still is where all planets eventually go. Once past the habitable warmth, a world cools into silence. Atmospheres thin. Seas evaporate or freeze. The crust cracks with dryness. Carbon dioxide fades or locks into soil. Winds lose their breath. The world becomes Mars-like, red, barren, preserved only by memory. In this cosmic theory, Mars is not an outlier but a preview, an elder sibling farther along the journey, showing all younger planets the future they are destined to meet. Thus the solar system is not a static family but a procession, Mercury-like infants near the Sun, Venus-like adolescents with smothering atmospheres, Earth-like adults warm and fertile, Mars-like elders cold and brittle, and beyond them the frozen giants, once perhaps temperate worlds themselves, now wandering ancient, quiet, and distant. The theory ends with a haunting notion: the Sun has always birthed worlds, and worlds have always fled, and perhaps one day our own Earth will be nothing but a whisper of warmth in an ever-cooling orbit. For now, though, the planets continue their slow outward march, climbing a ladder of heat and time, one rung at a time, from fire to stone to ice. Chapter 2, The Lost Civilizations of the Red Dawn. Long before Earth cooled enough to draw its first breath, long before oceans formed or continents cracked, another world basked in the perfect warmth of the sun. In the ancient version of the drifting world theory, Mars was once the true cradle of life, not the frozen, red desert humanity sees today, but a vibrant blue-green sphere orbiting where Earth now resides. It was a world rich with rivers, storms, plains of jade grass, and mountain ranges softened by warm, humid winds. Whether nature shaped it alone or intelligence shaped it further, Mars was believed to have been alive. The Martian year was shorter then, its daylight more golden, its skies a softer shade of cyan than Earth's present blue. With a thicker atmosphere and stable climate, it may have supported forests of towering mineral-rich trees whose leaves shimmered with faint metallic hues. Early astronomers who followed this theory imagined oceans teeming with strange aquatic life, translucent creatures that communicated by flickering bioluminescent patterns, and massive armored beings that fed on thermal vents. On land, ecosystems evolved under a gentler sun, giving rise to intricate forms that would one day vanish without a trace. Among these possibilities, the theory always speaks of one species in tones both grand and mournful, the first people of Mars. They were not humans, but they may have been humanoid in form, tall, thin, adapted to a lighter gravity. Their cities were said to be carved into canyon walls and shaped from the planet's naturally occurring iron-rich stone. They harnessed geothermal energy from beneath vast plains and built observatories that tracked the shifting motion of their own world, slowly sliding outward from the sun, century by century. According to this tradition, the Martians were the first to discover that their planet was drifting. At first, the change was so subtle that only their most brilliant astronomer suspected it. Then, as millennia passed, the migration became undeniable. The sun grew fainter. Seasons stretched. Winters lengthened and clawed deeper into the equator. Their oceans began to shrink. Winds intensified as the planet cooled, carrying fine red dust that settled everywhere, on their homes, on their monuments, on their very skin. As the global temperature declined, the atmosphere thinned. Gases that once warmed the world froze out of the air or escaped into space entirely. Lakes cracked like shattered glass. Rivers faded into winding scars. Life retreated, some species migrating underground, others dying out entirely. The Martians fought desperately for survival, sealing their cities, creating protective domes, trying to trap heat and preserve precious air. But the outward drift was relentless, and nature always claims her due. Eventually, the first people faced a truth they could not ignore: their world was crossing the threshold from warm to cold, from living to dying. In the final age of the Red Dawn, they watched as dust storms, once seasonal, became permanent spectacles, choking the sky and dimming the light that remained. Their history, engraved in stone and metal, recorded the growing despair. Technology could prolong survival, but it could not halt the cosmic march carrying their planet farther into the shadows. The theory ends their story with uncertainty. Some say the Martians perished with dignity, leaving behind ghost cities buried beneath dunes. Others believe they fled, perhaps to Earth when it was still cooling, or to the moons above, seeking refuge among the stars they had studied for so long. But by the time Earth rose into the sun's sweet, temperate zone, Mars had already become a skeletal world. Its seas were gone. Its winds carried only dust. Its once thriving civilization had vanished, leaving behind silence and red desolation. Today, as rovers crawl across its barren surface, they trace the echoes of an ancient world that might once have flourished. And in this drifting world theory, the lesson is sobering: what Mars is now, Earth will one day become. Every world walks the same path, from fire to bloom to frost, as it slides slowly, inevitably, away from its creator. Chapter 3: Venus in the Temperate Zone. If Mars represents the memory of what a warm world once was, Venus represents what a young world might become, if given enough distance and enough time. In the drifting world theory, Venus is seen as a planet caught in an early, feverish stage of its evolution, a world wrapped in toxic heat, smothered by its own atmosphere, and trapped too close to the Sun's overwhelming embrace. But it was not always doomed to be this way. According to this cosmic narrative, Venus is simply at the beginning of the journey every planet must take, the molten adolescence before stability, before oceans, before life. Venus today is a world of extremes. Its clouds are made not of water, but of sulfuric acid, a dense, choking veil that hides the surface beneath in perpetual twilight. The pressure at the ground is crushing, more like the depths of an ocean than the surface of a terrestrial world. And above all, Venus is unimaginably hot, hot enough to melt lead, hot enough to erase any possibility of liquid water, hot enough that even its mountains shimmer under the weight of radiant heat. This furnace-like condition is the result of the runaway greenhouse effect, where thick layers of carbon dioxide trap heat with merciless efficiency. Once this process began, it fed on itself, warming the planet, evaporating any remaining water, and making the atmosphere thicker still. In the drifting world theory, Venus is understood as a young version of Earth, not in its surface habitability, but in its position within a planetary life cycle. It is what Earth could have been had it drifted closer instead of staying in balance. But the same mechanism that once overheated Venus may someday save it. As planets move slowly outward in their solar orbits, their exposure to sunlight decreases. Over millions of years, Venus too would drift, cooling degree by degree, century by century. And if the planet ever passed into Earth's temperate zone, the transformation could be profound. If Venus entered Earth's orbit, the first and most dramatic change would be the slow loss of heat. The greenhouse effect would not end immediately, its atmospheric blanket is far too thick for that. But as solar input weakens, the upper atmosphere would begin to condense and shrink. Winds would calm. The sulfuric acid clouds would gradually dissipate or fall as corrosive rain, clearing the skies for the first time in billions of years. Reduced temperatures would cause carbon dioxide to react with cooling basaltic rock, forming carbonates and drawing the gas out of the air, thinning the atmosphere layer by layer. Over geological time, this process could trigger the most important shift of all, the possibility of water. Not oceans at first, only droplets, or thin mist, or transient pools in sheltered basins. But to a world long starved of moisture, even this would be a revolution. As temperatures continued to fall, the surface might cool enough to allow stable liquid water to form. Rivers could eventually carve valleys. Steam could condense into true clouds. The atmosphere, once a suffocating cloak, might finally become transparent and breathable, not to humans, perhaps, but to emerging ecosystems with time to adapt. And as Venus settled fully into Earth's orbital zone, it would resemble a young Earth more closely than ever. Volcanic activity would stabilize. The crust would become less volatile. Chemical cycles would develop predictable rhythms. If seeded with life, naturally, accidentally, or even by intelligent intervention, Venus might begin to host primitive organisms. Over tens or hundreds of millions of years, these could reshape the atmosphere further, gradually turning a cooling hellscape into a thriving world. In this theory, every planet has a moment in the sun's sweet spot, a brief equilibrium where temperature, atmosphere, and chemistry align to create the conditions for life. Earth occupies this moment now. Mars once did. And Venus, in time, may grow into it. The planets are not static, not fixed in destiny. They are travelers passing through stages of warmth and cold, decay and rebirth. Thus Venus is not merely a warning of runaway heat, it is a preview of potential awakening. A world that today is uninhabitable could, under the right cosmic drift, become a future home for life. And in this grand solar cycle, every planet has its turn. Chapter 4: Earth's Brief Window of Balance. According to the drifting world theory, Earth exists in a fleeting moment, a narrow, precious interval during which conditions are neither too hot nor too cold, neither too violent nor too barren. It is a pause in a much longer cosmic migration. Earth has not always been this temperate, and it will not remain so forever. Like Mars before it, and Venus after it, our world is simply passing through the sun's habitable zone, carried outward by forces too gradual for any human lifetime to perceive. Right now, Earth appears perfectly tuned for life. Oceans shimmer with blue depth, continents breathe forests, deserts, and fertile plains. The atmosphere holds just the right mixture of gases to trap enough heat for stability without spiraling into catastrophe. This balance is delicate, impossibly so, and yet it persists, as though Earth occupies a golden resonance between scorching youth and icy old age. But beneath this apparent stability lies unmistakable evidence that our planet is shifting. The sun is slowly growing hotter with age, and Earth, in response, is drifting outward by tiny increments, a dance measured in centimeters per year but magnified across eons into a true migration. If the sun's gravity, solar winds, and magnetic interactions indeed impart outward pressure, Earth is already beginning to inherit the position once held by Mars, and to relinquish the position that Venus will one day approach. Scientists note that the sun brightens gradually over billions of years, and in the drifting world model, this brightening is one of the drivers forcing planets to adjust their orbits. Earth moves outward not quickly enough for humans to sense, but inevitably enough that the cradle of life is already becoming subtly cooler than it once was. Glacial cycles deepen. Deserts spread. Weather patterns shift. These changes are small now, whispers of a future transformation, but in the language of planets, the whisper is the warning. In its current stage, Earth sits in the middle of its life zone. The atmosphere is vibrant, full of oxygen generated by biological activity. Oceans are liquid and abundant. The sun's warmth supports ecosystems that range from the frozen poles to the humid equator. But this balance is transitional. As the drift continues, Earth will slowly lose heat. At first, the oceans will still moderate global temperature. Plant life will adjust. Species will evolve. But the long-term trend will be relentless. The planet will inch outward, cooling enough that its climate will become more volatile. The drifting world theory paints a haunting picture of Earth's far future. As solar energy reaching the planet declines, atmospheric gases will begin to behave differently. Carbon dioxide will be drawn down as plant life diminishes. Weather cycles will weaken. Clouds will thin across vast regions, making storms less frequent but more severe when they do emerge. The oceans, Earth's great reservoirs of heat, will cool and contract. Coral reefs and biodiverse shallows will disappear first, followed by higher latitude ecosystems that can no longer endure prolonged winters. Over millions of years, Earth will transition into its early Mars stage. Thin sheets of ice will begin forming in regions that were once lush. Forests will shrink into stunted pockets. Atmospheric density will decline as gases are absorbed, frozen, or lost to space. The planet will still host life, hardy, cold-adapted life, but its golden age will be ending. Eventually, Earth will drift far enough that oceans freeze permanently. The atmosphere will collapse into frost. Dust will scour the surface as winds weaken and landscapes dry into brittle, iron-colored deserts. What was once a world of green and blue will become a husk of red and gray. Mars is not a cousin to Earth. In this theory, Mars is Earth's future. Yet for now, Earth remains the jewel of its cosmic procession. It has not fully cooled. It has not yet grown barren. It stands at the zenith of its livable phase, a world in its prime, unaware of the slow migration beneath its feet. As Earth drifts outward, Venus will drift inward into our place, beginning its long journey toward becoming temperate. And behind us, Mars waits in the cold, its ancient secrets buried beneath dunes, monuments to what happens when a world's moment in the sun has already passed. Chapter 5: The Birth of a New World. The drifting world theory does not imagine the solar system as a finished sculpture, but as a living workshop, a place where the sun continues to forge new planets even as the older ones drift outward into their long cooling journeys. In this vision, the sun is both a furnace and an architect, forever reshaping its own body and sending fragments of itself into the surrounding void to become new worlds. These fragments, rare yet monumental, mark the beginning of the cycle, the birth of a Mercury. Every few 100 million years, the sun undergoes a period of turbulent instability. Deep within its core, magnetic fields twist into knots of unimaginable strength. Pressure builds. Plasma churns. And then, without warning, a titanic expulsion erupts from the solar surface, not a typical coronal mass ejection, but a catastrophic jet of molten star stuff, dense enough and cohesive enough that it does not dissipate like ordinary solar flares. Instead, this incandescent material arcs outward before gravitational tension snaps it loose, sending a vast, glowing mass spiraling into heliocentric orbit. At first, this newborn world is nothing more than a swirling ember of plasma and vapor. It stretches and contracts, rotating violently as it sheds heat into the vacuum. Its temperature is so extreme that even metals exist only as vapor, and the space around it shimmers with radiating energy. Slowly, over thousands of years, the glowing mass begins to cool, the outer layers thicken, forming a molten crust. Gravity gathers the material inward, smoothing the fragment into a sphere, the first recognizable shape of a planet. This early planet, still blistering and unstable, resembles a proto-Mercury, a world without atmosphere, hammered by solar radiation, its surface a chaotic ocean of magma. Volcanoes taller than continents erupt continuously, reshaping the crust faster than it can solidify. Rivers of liquid metal flow across plains of cooling basalt, only to remelt in the next surge of heat. No clouds form here. No water. No stable air. Even the faintest wisp of gas is immediately torn away by the sun's ferocious winds. Yet this stage is temporary. The new world occupies the innermost region of the solar system, a place where planets are forged but cannot remain forever. Over eons, the same forces that push all worlds outward begin acting on this infant planet. Gravitational interactions with the sun's rotation, coupled with solar wind pressure and magnetic resonance, subtly widen its orbit. The process is agonizingly slow, imperceptible to any observer not living for millions of years, but unyielding. Like a cooling ember rolling away from a campfire, the young planet begins its long march outward. As it drifts, something remarkable happens. The planet starts to cool enough to hold onto small traces of gas. Minerals in the crust release vapors that are no longer instantly stripped away. The surface solidifies into jagged terrain. Mountain ranges rise from tectonic contractions. Craters from early impacts remain scorched into its face. It is still hostile, still lifeless, still a world made of fire and stone, but it has begun to take its first steps toward transformation. In the drifting world theory, this is the birth cycle of planets. They are not formed all at once, but continuously, slowly, and painfully from the sun's own body. Each new world begins at the frontier of heat, where no atmosphere can survive and where the raw materials of geology are still molten and restless. Only time, distance, and cooling can sculpt such a world into something like Venus, Earth, or Mars. The theory proposes that at this very moment, somewhere near the sun's blazing limb, the seeds of the next Mercury may already exist, a knot of plasma accumulating mass, rotating faster than the surface around it. It is not yet a world, not yet solid, not yet separate. But in the language of stars, it is a promise, a hint of the next planet to join the outward procession. For planets are not permanent fixtures. They are chapters in a story the sun has been telling since the dawn of time. And with every outward drift, every cooling stage, and every transformation, another chapter begins. Chapter 6, The Veiling of the Young World. Millions of years pass, and the newborn planet drifts ever so slightly away from the sun's smoldering grasp. What began as a molten shard of starfire slowly becomes a solid world, still hostile, still scorching, but no longer liquid in its entirety. Its crust hardens into continents of blackened basalt. Impact craters remain preserved as glowing scars, slowly dimming as the planet bleeds heat into the expanding darkness around it. The violent eruptions that once defined its every moment begin to subside, volcanoes still roar, but with longer intervals between their fiery breaths. The world is stabilizing, and with stability, a new transformation begins. As the surface cools, minerals and metals lock deep within the crust release vapors, sulfur, carbon dioxide, carbon monoxide, and faint traces of water vapor. Alone, these gases would be negligible, instantly torn apart by solar winds or eliminated by the planet's still hot crust. But the world is drifting outward, and distance grants protection. For the first time in its existence, thin wisps of atmosphere cling to the surface, swirling into hazy tendrils that thicken with each passing millennium. This is the birth of a Venus-like stage, the veiling phase, when a young planet dons a thick, suffocating cloak of gas. Volcanic activity becomes the primary architect of the atmosphere, belching out carbon dioxide in volumes that dwarf anything Earth would later experience. Sulfur compounds rise into the sky, forming dense clouds that trap heat with brutal efficiency. As soon as the planet's distance from the sun allows even a hint of retention, these gases accumulate with explosive speed. The greenhouse effect begins its merciless ascent. The atmosphere balloons, tens then hundreds of times denser than anything breathable. Sunlight struggles to pierce the thickening veil, its rays scattering and heating the upper layers before ever reaching the ground. Pressure mounts to levels that crush rock formations and cause liquid metals to flow beneath the crust like slow-moving serpents. Lightning storms rage through sulfuric clouds, illuminating the sky like an eternal, flashing bruise. Winds howl across the surface, sculpting mountains of ash and carving valleys of stone softened by heat. Despite its hostility, this stage represents the first true stabilization of the New World. Unlike the violent infancy of molten oceans and explosive volcanism, the veiling phase is structured, predictable, almost rhythmic. Atmospheric cycling replaces surface chaos. Temperature gradients stabilize. Volcanic outgassing balances with atmospheric absorption. Even if alien to life as humans know it, the planet is becoming an integrated system, a proto-Venus with the potential to continue evolving. The drifting world theory suggests that all rocky planets spend time in this phase, lingering in a state of crushing heat and opaque skies before cooling enough to transition toward temperate conditions. Venus, currently trapped in this stage, is simply too close to the Sun for its veil to thin. But the world born from the Sun's molten eruption is slowly moving outward, and its atmosphere, though thick, violent, and blazing, is not destined to remain this way forever. As the planet continues its migration, the balance begins to shift. With increasing distance from the Sun, the thick sulfuric clouds begin to condense more often than they evaporate. Layers of gas descend into the atmosphere, creating stratified currents that raise the possibility of long-term cooling. Volcanism calms further, slowing the rate at which new greenhouse gases replenish the sky. The surface temperature drops, not dramatically yet, but enough that the most extreme atmospheric reactions diminish. Something extraordinary is beginning, the first whispers of potential habitability. Though still impossibly hot and toxic, the world is on a long trajectory toward a future that may resemble Earth's. Oceans do not yet exist, but water vapor is slowly increasing. Atmospheric pressure remains crushing, but it is no longer escalating uncontrollably. The planet trembles at the edge of its next transformation, a transformation that will require millions more years of drift, cooling, and geological maturation. In the cosmic procession, a new Venus has emerged. But its destiny is not to remain a furnace. As the world continues outward, a calm will eventually come. Clouds will thin. Heat will release. The veil will begin to lift. And in this lifting, a miracle will unfold, the transition into a blue, life-bearing world, the Earth stage. Chapter 7, The Blue Awakening. The drifting young world, once molten, then veiled in suffocating clouds, continues its gradual escape from the Sun's most punishing heat. Over tens of millions of years, its orbit widens just enough for temperatures to fall below catastrophic thresholds. Though still hot, the world begins hovering in a precarious balance between sweltering and survivable. This is the threshold every planet must cross if it is to become something more than a furnace or a frozen husk. This is the moment when a world enters the blue awakening. Slowly, almost imperceptibly, the dense carbon dioxide atmosphere begins to change. The crushing pressure remains immense, but cooling crust minerals start reacting with binding it into carbonate rock. Every small reduction in greenhouse gas allows heat to escape more easily into space. The sulfuric acid clouds that once reflected sunlight and trapped infrared heat now condense into thicker layers that settle toward the surface as acidic rain. Over time, this chemical downpour neutralizes against the cooling rocks, releasing small pockets of water vapor that no longer instantly evaporate. And then, on a timeline too grand for any species to witness, the first miracle occurs. Water becomes liquid. Thin sheets form in the deepest basins, first ephemeral puddles, then shallow pools. The sky, though still hazy, grows brighter as clouds begin to separate into layered formations rather than a single unbroken blanket. Rainfall shifts from corrosive sheets to gentler, mineral-rich droplets that carve new patterns into the rock. The world exhales for the first time in its existence, releasing plumes of steam that drift upward to form clouds that carry water, not acid. Oceans come next. As the atmosphere loses mass and heat escapes, vast amounts of vapor condense. Rains fall for thousands of continuous years, filling the hollows of the crust, cooling the mantle below, and creating the first global hydrosphere. What was once an inferno becomes a planet of shimmering blue, its seas glowing with volcanic minerals, its early skies shifting from orange to pale gold. Lightning still cracks violently in the atmosphere, but instead of igniting sulfur storms, it now fertilizes the newborn oceans with reactive compounds. The planet has entered its Earth-like stage, though it is not yet Earth. It is younger, wilder, a world in its adolescence, full of energy but transitioning toward balance. The greenhouse effect remains present, but mild enough to keep temperatures stable. Winds calm from hurricane-force gales into steady global currents. Seasons begin to form as the planet's rotation and tilt interact with sunlight in more predictable patterns. And with this newfound stability comes possibility. Shallow oceans teem with chemical potential. Hydrothermal vents release complex molecules that collide, bond, break apart, and reform in endless cycles. The atmosphere now contains nitrogen, carbon dioxide, water vapor, and trace gases, an alchemical mixture ripe for the spark of life. Whether life emerges spontaneously from these reactions or arrives on meteoritic fragments from older planets, the world is finally ready to host it. Green begins to appear long before forests. Mats of primitive organisms coat shorelines and shallow waters. Photosynthetic life slowly, steadily changes the atmosphere, adding oxygen in faint quantities that accumulate over millions of years. The planet's surface becomes more varied, volcanic islands rise, erode, and seed nutrients into the sea. Continental plates shift, forming the first landmasses large enough to influence climate. It is a planet at peace, poised between fire and frost, a world in its prime. In the drifting world theory, this is the most precious phase of any planet's life, its habitable window, where conditions align so perfectly that life can flourish. Earth exists in this window now, sustained by oceans, a stable atmosphere, and a sun neither too distant nor too intense. But like all chapters, this one does not last. The drift continues. The world inches outward still. Its oceans, though vast, are temporary. Its warmth, though comfortable, is borrowed time. For every world that becomes blue, another eventually becomes red. Still, in this chapter of its existence, the world thrives. It is a jewel in the cosmic procession, a world that will one day cool into desert, then dust, then silence. But that future lies far ahead. For now, the planet basks in the golden age of life, the stage every world hopes to reach, and the stage every world must someday leave behind. Chapter 8: The Long Descent into Dust. The golden age of the young blue world lasts longer than any species could comprehend. Entire eras rise and fall beneath its temperate skies as oceans pulse with life and continents breathe forests, plains, and vibrant ecosystems. Yet the drifting continues, relentless, patient, irreversible. Inch by inch, century by century, the planet moves outward from the sun, the warmth that once sustained it slowly fading into a distant, muted glow. At first, the changes are subtle. Winters lengthen, becoming harsher with each passing epoch. Glacier creep from the poles, descending upon once fertile lands. Mountain ranges are carved by advancing ice, and the great forests retreat toward the equator, seeking refuge in shrinking belts of warmth. Storms become more erratic, driven by the unstable gradients forming between cold poles and lukewarm tropics. Life adapts, but it adapts unevenly. Some species flourish briefly in new niches, others vanish without leaving fossils behind. The oceans are the first unmistakable casualties. As global temperatures drop, evaporation rates plummet. Rainfall diminishes. The water cycle slows to a crawl. Sea levels begin their millennium-long retreat, exposing vast continental shelves that quickly dry and crack under thinning air. Coral reefs crumble and bleach, then fossilize. Marine life retreats into deeper basins where volcanic vents offer the last pockets of warmth. What were once deep blue waters turn murky green, then brown, and finally pale as sediments settle in lifeless calm. Atmospheric transformation follows. Plants, struggling to photosynthesize under dimmer sunlight and weaker carbon dioxide availability, diminish year by year. With their decline comes a decrease in oxygen production. The air grows thin, not enough to suffocate instantly, but enough to alter climates globally. Winds weaken, unable to maintain the strength they once had in a thicker atmosphere. Weather systems collapse into simpler, more predictable patterns, long, frigid nights, weak daytime breezes, and increasingly rare storms. Volcanism, once the beating heart of the planet's heat exchange, grows quiet. Tectonic activity slows as the mantle cools. Mountain building ceases. Erosion flattens the surface into a wide, desolate plain interrupted only by the skeletons of ancient ranges. The cooling crust contracts, fracturing into deep canyons that leak gases into the shallow air, but not fast enough to rebuild what is being lost. Then comes the pivotal moment in the planet's downfall. The oceans freeze. Not all at once, but in creeping masses of ice that expand across the globe. Ice sheets reach the equator. Only pockets of liquid water remain beneath thick shells, heated by the last fading hydrothermal vents. The surface becomes a mosaic of red, brown, and white, dust-covered ice, exposed barren rock, and oxidized minerals that stain the world in Martian hues. As ice locks away the remaining water, atmospheric pressure plummets further. Carbon dioxide freezes out onto the poles, forming dry ice deposits that glitter faintly under a pale sun. The once thick atmosphere collapses into a thin whisper. Sound carries poorly. Winds lift only the finest particles of dust, creating slow, ghost-like storms that drift across the landscape with eerie silence. Life dwindles to extremophiles, microbes sheltered deep underground, clinging to fading warmth left over from the planet's youth. Eventually, even these begin to die as geothermal energy dissipates and chemical gradients flatten into stillness. The world enters its Mars stage. Dry riverbeds stretch across empty plains. Canyons and ravines remain as monuments to ancient water. Salt flats, once shallow seas, glitter like shattered glass. The sky, once blue, becomes a muted pink or faded copper as fine dust particles scatter the weakened sunlight. Temperatures drop so low that dawn feels indistinguishable from dusk. Civilizations that might have arisen during the planet's warm phase, if they existed at all, would have vanished by this point, leaving behind only ruins, eroded beyond recognition. Time erases their footprints. The dust claims everything. Eventually, the world becomes indistinguishable from the Mars humanity knows today, a cold, thin-aired desert, a memory of life carved into stone patterns, waiting in silence as it drifts farther and farther from the fading warmth of its creator. This is the destiny of all worlds in the drifting theory. After the Blue Age comes the Red Age. After the Red Age comes silence. And after silence comes only the slow outward glide into eternal cold. But even as this planet descends into desolation, the sun continues its ancient cycle. Another eruption brews. Another molten fragment coils on the solar surface, ready to break free. The universe balances endings with beginnings. Chapter 9: The Elder Worlds at the Edge. In the drifting world theory, the solar system is not a neatly stratified collection of planets, asteroids, and icy bodies, but a timeline, a grand procession in which each world represents a different age, a different chapter of solar evolution. The innermost planets are newborns, raw and hot. The middle planets are adolescents and adults in their blue, life-bearing phase. The outer planets, cold, red, frozen, are elders. And beyond them, far past the traditional orbits, lie the ancient ones, the forgotten worlds. These distant objects, Pluto, Eris, Makemake, Haumea, Sedna, Quaoar, and countless unnamed icy rocky bodies, are seen in this theory not as failed planets or mere debris, but as the oldest terrestrial worlds in the solar system. They are planets that once thrived close to the Sun in ages so distant that even Earth had not yet been born. Over billions of years, they drifted outward into the dim frontier where starlight is weak and warmth almost non-existent. According to this model, Pluto and its kin did not begin icy. They began much like the young Mercury-like worlds of Chapter 5, molten, turbulent, and violently active. They would have passed through every evolutionary stage, the veiled Venus stage, the blue Earth stage, the red Mars stage, and eventually the frozen extinction stage. Each transformation marked their slow retreat from the Sun, driven by the same outward forces affecting all planets. But where Mars stopped and froze into desert, these elder worlds continued drifting. The further they moved, the colder and quieter they became. Oceans froze solid. Atmospheres collapsed and settled onto their surfaces as thin frost layers. Gravity weakened with distance, allowing precious gases to escape into space even faster. Volcanism dwindled, then died. Eventually, the worlds arrived in the Kuiper Belt, an enormous graveyard of worlds that had completed the entire planetary life cycle. Their surfaces now tell the story of extreme age. Frozen nitrogen and methane form plains smoother than polished marble. Ancient impact basins survived unmelted, preserving craters billions of years old. Cracked crusts hint at once active interiors long cooled into silence. Thin atmospheres, like Pluto's faint nitrogen halo, appear briefly when sunlight warms them, ghost remnants of once thick, life-supporting envelopes. To the drifting world theorists, these characteristics are not signs of primitive formation, but the exact opposite, signs of ancient completion. These are worlds at the end of their evolutionary arc. Pluto, in this model, may have once circled the Sun at a distance similar to Venus or Earth, basking in warmth, hosting oceans of liquid water, and experiencing seasons, winds, and weather patterns. If life ever arose there, it would have perished as the planet drifted outward, first freezing its oceans, then collapsing its atmosphere, and finally locking all activity beneath a miles-thick crust of ice. Sedna, even farther away, might be older still, perhaps one of the first planets ever ejected from the inner solar system after the Sun's earliest eruptions. Now it wanders on an elongated orbit so vast that its year lasts tens of thousands of Earth years. It is a relic from a time before Earth existed, a fossil planet encased in nitrogen and methane ice. To drifting theorists, the asteroid belt itself may be a transitional zone, a place where multiple rocky planets broke apart during their cooling phase or during gravitational conflicts with larger migrating worlds. These fragments remain as reminders of how many planets the Sun may have once birthed. In this cosmic narrative, the Kuiper Belt is not a cold wasteland but a retirement home for planets. Worlds that once burned with volcanic fire. Worlds that once glowed blue with oceans. Worlds that once breathed atmospheres. Worlds that once may have sustained life. But no longer. Now they orbit silently on the far edge, their surfaces etched with the wrinkles of geologic time. They are too cold to melt, too ancient to change, too distant to revive. Their existence is a solemn reminder of what all planets eventually become, including Earth. For the planets born from the Sun are like embers blown from a fire. At first they burn. Then they glow. Then they fade. And eventually, they slip into darkness. The elder worlds at the solar system's edge are those faded embers, ancient, frozen, and nearly forgotten, but still carrying the faint scars of a fiery past. Final chapter: The Weight of a Cosmic Theory. The drifting world theory, bold and sweeping as it is, offers a way of understanding planets not as static entities but as participants in a vast, slow migration from fire to frost. It proposes that Mercury-like worlds are newborns, Venus-like worlds are maturing, Earth-like worlds are thriving, Mars-like worlds are fading, and the icy Kuiper objects, Pluto, Sedna, Eris, are the ancient dead, the final stage of planetary evolution. The idea is elegant, almost poetic. Every world follows the same path, and the solar system contains planets of every age to prove it. But how much validity could such a theory hold? From a scientific standpoint, the drifting world concept stretches beyond accepted astrophysics. We know planets form early, not continuously. We know the Sun sheds plasma but not intact planetary masses. We know orbital drift occurs, but only subtly, and not enough to send planets sweeping across the solar system in clear evolutionary arcs. The idea that Venus will someday cool into an Earth, or Earth will freeze into a Mars, departs from traditional models of celestial mechanics. And yet, the story this theory tells matches an undeniable truth. Everything in the solar system is changing. The Sun is growing hotter with age. Earth will warm, then eventually cool once the Sun consumes its hydrogen and swells into a red giant. Mars was warmer and wetter long ago. The outer icy worlds do bear the scars of ancient geologic activity. Planets do migrate in early formation. Stars can eject massive streams of plasma that may condense into bodies. Across the long sweep of cosmic time, the line between poetic theory and plausible celestial evolution becomes thin. Even if the drifting world theory isn't literally accurate, its metaphor may be profoundly true. Every planet has a window, a season of life. None remain habitable forever. For humanity, this realization carries immense weight. If Earth is in its golden middle age, a brief oasis between Venusian heat and Martian cold, then our species is living in the rarest and most precious slice of planetary time imaginable. Earth is warm, oxygen-rich, water-filled, and stable. This balance won't last forever. Even conventional science agrees that Earth's habitability will decline as the Sun brightens, long before it becomes a red giant. the drifting world narrative amplifies this truth. Civilizations rise on warm planets, but those planets inevitably drift outward into cold silence. If that is so, then humanity faces a choice shared by every intelligent species the universe might ever know. We either learn to move faster than our world drifts, or we fade with it. The theory suggests that once a planet slips into its Mars stage, recovery is impossible. Atmospheres collapse. Water freezes. Life dies. If civilizations wait until those signs emerge, it will be far too late. But if we learn from the planets that came before, if Mars truly was once like Earth, if Pluto once held oceans, if the Kuiper Belt holds the corpses of forgotten worlds, then humanity has a warning written across the solar system in ice and stone. No planet stays alive forever. What does this mean for our survival? It means humanity must learn to expand, to migrate before the planet cools, to adapt to new worlds or artificial habitats, to develop technologies capable of sustaining life independent of Earth's fragile equilibrium. If life is a fleeting phase in planetary evolution, then the only way to preserve it is to carry it forward, like torchbearers running ahead of the dying light. In that sense, the drifting world theory, whether physically accurate or symbolic, gives humanity a mission. Explore Mars not just to understand it, but to learn from its fate. Study Venus not to fear it, but to foresee what happens when climates run wild. Investigate Pluto and the outer worlds as relics of planetary death, reminders of what lies ahead in deep time. Prepare for a future where Earth is no longer enough. The solar system, according to this story, is a timeline of planetary past, present, and future. We stand in the middle of that line, not at the beginning, not at the end, but at the brightest, most fragile moment. The sun birthed the worlds. The worlds drift outward. Life blooms briefly in the balance. Then the cold comes. Humanity's survival depends on understanding this rhythm, and learning to break free of it. For if planets cannot outrun their destiny, perhaps their children can. The end.